My name's Matthias Gondan. I'm a lecturer at the Department of Psychology at the University of Copenhagen. This is a pre-recorded presentation for the 2020 meeting of the Society for Mathematical Psychology. The topic is testing the race model in a difficult redundant signals task. The presentation deals with a 150-year-old problem, already pointed out by Fechner in 1868. Is there a way to deal with incorrect responses in response time measurement? As you can see on the right, Fechner's response was basically no. And indeed, in current research on cognition, we see basically two schools. One group, let's denote them as attention researchers, uses response time measures in their experiments. Because they don't know how to deal with the wrong responses, they use very easy tasks, or let's face it, rather boring tasks, so that accuracy is basically 100%. The other group, let's call them memory researchers, they use actually quite demanding tasks, but because they don't know how to analyze speed in the presence of wrong responses, they focus on accuracy. And then, of course, there's the minority of mathematical psychologists doing rather weird experiments to which they feed dubious models with strange parameters. I will not focus on them today, but I want to look into this corner on the right, measurement of response times in the presence of wrong responses. But before we start, I would like to recall that if we use response time as a performance measure, a good response is fast and correct. If you order a pizza, you want it to be delivered fast, and you want the one with the mushrooms, not the one with the cheap salami on it. So what happens in mainstream experimental psychology? In fact, incorrect responses, omitted responses, fast guesses, and all sorts of problematic behavior are typically excluded from the analysis. Here you can see an overview from the Journal of Experimental Psychology in issue 1 in 2013. And basically all the studies use the mean correct RT, which is the mean response time, given that the response was correct. In other words, we have a mismatch between the theory and the data analysis. Theory says good performance means fast and correct. Data analysis says fast if correct. For the pizza example, the theory says I want the pizza delivered fast and I want the right one. The data analysis says if you bring the right pizza, please hurry up. If you bring the wrong pizza, let's forget about it. I think the pizza example nicely illustrates that one really shouldn't do this kind of analysis. How should we analyze the data instead? Let's focus on a redundant signals task, which is a very basic experimental setup in multisensory research and more generally in research on cognitive architecture. In this task, we have stimuli of two sources, for example, auditory and visual. And the important aspect is that the same response is required to these stimuli. We have three conditions: auditory, visual, and both stimuli together, which is the redundant stimulus. The typical finding is a redundancy gain that is faster responses in AV than in A and V alone. This redundancy gain can arise from two classes of mechanism. One is real integration of the information of the two sources. This is often called co-activation and yields faster responses to AV by some kind of pooling or whatever. Whereas the other one is more relevant here. This is the so-called race model. Here, processing of the two channels is in parallel. They run against each other, and the minimum, which is the faster of the two channels, determines the response. Like tossing two dice and choosing the one with a lower number of pips. In this model, we only see more fast responses to the redundant stimulus, which of course gives us faster average response times. The redundancy gain by the race model has an upper limit given by Miller's race model inequality. I'll shortly derive it here to familiarize you with the notation. We have the random variables denoting the processing times of the two channels, dA and dV. These are assumed to be invariant over experimental contexts, meaning that dA has the same distribution in A and AV and the same for dV. And here I omit any residual processing times, for example, due to the finger movement or so. In the single stimuli, the channel-specific processing times directly translate to the observable response times. For the redundant condition, the observable response time is the minimum of the channel-specific processing times. And this minimum is below some t if either dA is below t or dV is below t. We can then apply Boole's inequality to obtain the upper bound of the probability for this union of events. And then by assumption of context invariance, we can relate these probabilities under AV to the respective events in the single stimulus conditions, which gives us the race model inequality as published by Miller in 1982. For today's purpose, I'd like to repeat the derivation in a slightly different way, distinguishing the two mutually exclusive cases that dA wins the race, then TAV, the response time in the redundant signals condition is dA, and if dV wins the race, the latter determines the response time. The probability for these two mutually exclusive cases, for the union of these two mutually exclusive cases, is just added up. You can see this here. And then we drop the conditions for the cases which we cannot observe anyway, which gives us the upper bound again from the race model inequality. So let's say we have an experiment with simple responses, 100 trials in each condition, and we see 20% fast responses in A, 20% fast responses in V, and 50% fast responses in AV. Then the race model inequality would be violated, and we would conclude that some kind of co-activation is responsible for the redundancy gain. I will not go into further details. This has been discussed elsewhere. Today's topic is whether we can generalize the derivation of the race model inequality to more demanding tasks. So we are now looking into this corner here. Each channel is now associated with a pair of random variables, processing time d and accuracy c. And again, in the single stimulus conditions, this directly translates to the observable response time and accuracy. In the redundant condition, we again distinguish the two cases that channel A wins the race. In that case, dA and CA determine the response, or whether dV wins the race and then the other two variables determine the response. So if we look, when is a response a good response, for example 1, then we would just add the restriction CA equals 1 and CV equals 1 to the whole derivation, and nothing changes in principle. Illustrate this by an example. So we have an experiment with choice responses. For uppercase A, V, and AV, response 1 is required, whereas for lowercase AV and AV, response 2 is required. This could, for example, be weak and strong stimuli. Let's say in condition uppercase A, we see 20% of responses that are fast and 1. The other 80% responses are either slow or 2 or both. And the same in condition uppercase V. And in the condition uppercase AV, we would have 50% of responses being 1 and fast. And again, the race model would be violated. We could do the same for the lowercase conditions and response 2. And we could do the same for wrong responses. So for example, uppercase AV and AV and response 2. So let's say we have 5% wrong responses to A, 5% wrong responses to V, and 15% wrong responses to AV. That would be a violation of the race model prediction. The same could be done for a go-no-go task. So race model inequality is violated if 20% of the uppercase A stimuli are correctly detected. The same for uppercase V and 50% for uppercase AV. And we could even have a violation of the race model inequality if we see 5% false alarms in lowercase a. That would be the no-go A. 5% false alarms in no-go V, and 15% false alarms in no-go AV. And one last thing that relates the new inequality to Miller's original work. Let's say we have again choice responses and we see 20% fast responses to uppercase A. Some of them are correct, some of them are wrong. We don't care. The same for uppercase V. 20% of responses are fast, regardless of whether they are correct or wrong. And 50% responses to AV are below 300 milliseconds, again, regardless of whether they are correct or wrong. That would again be a violation of the race model inequality. So you can see there's numerous new applications for experiments which have more demanding tasks than the boring simple response task, which is often used for redundant signals task. Remember again, you want the pizza delivered fast, so it's still warm, and you want it the one with the mushrooms. So whenever you use RT as a performance measure, keep in mind that good responses are fast and correct, not fast if correct. So if we have 100 responses to A and 20 of them are correct and below 300 milliseconds, 60 are correct and slow, and 5 and 15 are wrong. The proportion of good responses is 20 of 100, 20%, not 20 of 80, for example. That is fast if correct. That's it. Thank you. If you're interested in the details, have fun with our recent paper on this topic. Thanks to the Independent Research Fund Denmark for financing this. And I'm looking forward to interesting questions and an interesting discussion.